Okay, in this lesson we're going to be talking about our inverse trig functions. So let's start off by thinking about remembering what an inverse function is in the first place. So graphically, an inverse function only exists when our original function is 1-to-1. So when we can do both the horizontal line test and the vertical line test. Okay, so if we have a parabola, it passes the vertical line test. It only hits each line once, but it fails the horizontal line test. So our parabola or our quadratic functions do not have inverses. If we look at something like a cubic function, it passes both the vertical line test and the horizontal line test, so a cubic function would have an inverse. And remember, to find the inverse graphically, we would just reflect that graph about the line y equals x to find our inverse. Okay, so now let's take what we remember from inverse functions and apply that to our trig functions. We've had some good practice with graphing all 6 of our trig functions. Let's look at just our basic 3, our sine, cosine, and tangent. Now looking at each of these functions, are they 1-to-1? Okay, if I were to do the horizontal line test, nope. Cosine, nope. And tangent, nope. So all 3 of them do not have inverses as we're used to graphing them. So in order to look at the inverse of a trig function, what we've got to do is we've got to restrict the domain of each one in order for their inverses to be functions themselves. Okay, so we're going to go one by one. Let's start off with our sine function. So if we take just one little piece of our sine function, so let's say we're going to look at just the piece of our sine function from negative pi over 2 to positive pi over 2. Okay, so looking at our graph here, we're just taking this chunk here, and then we're going to place it on this graph. And this piece of our sine function is 1-to-1. We could do any vertical line, any horizontal line is only going to pass in one unique point. Okay, so we restrict our domain from negative pi over 2 to positive pi over 2, including both of those values. Okay, and our range for that piece would be from our minimum at -1 to our maximum at +1. Okay, so if we wanted to find the inverse of that piece, then we would flip our x and our y coordinates, reflect it over the line y equals x, and here's what we would come up with. We would come up with our function y equals the inverse sine of x. Okay, so we've got a beginning point at -1, negative pi over 2, still goes through the origin, and an end point at 1 pi over 2. Okay, remember with inverse functions, the domain and the range switch places from the original to the inverse. So if we want to look at the domain and range of our inverse sine function, well, our domain is now from -1 to +1. And our range goes from negative pi over 2 up to positive pi over 2. Arc sine is often used pretty much synonymously with our inverse sine. So for our purposes, inverse sine of an angle x or of a number x and arc sine of a number will mean the same thing for our purposes. So this is kind of interesting. So the inverse sine of a number. So whenever we take the inverse sine of a number, what we're really looking for, what it really means is what angle has that sine value. And more specifically, what angle between negative pi over 2 and positive pi over 2. Since that's our range, those are the only angles that can come out of our function. Those are the only angles that we're looking for that have that particular sign. So for example, if we were given a problem that said, what is the inverse sine of root 3 over 2? Okay, so we would go to our unit circle and looking for sine of root 3 over 2. So remember our sine values associated with our y values. Okay, and our angles that come out of our inverse sine are only in this first quadrant from 0 to pi over 2 and in a sense in our fourth quadrant, but these are our negative angles. So we wouldn't take them straight from our unit circle. We would start at 0 and go in the negative direction to negative pi over 2. Okay, so this sign would be positive. So pi over 3, or in degrees, 60 degrees. So this would be equal to pi over 3 if you're asked for it in radians, or 60 in degrees. Okay, next up, let's look at our inverse cosine. So if we start with our cosine function, and we restrict it from 0 to pi. So we're just going to take this chunk of our domain from 0 to pi of our cosine function. Then we've got a one-to-one function, so we can take the inverse of it and still get a function out. Okay, so note we're restricting the domain of cosine to 0 to pi. All right, so here's what our inverse looks like. Now our domain is what our range was from -1 to 1, and our range is what our domain was from 0 up to pi. Okay, so here's the graph of our function y equals the inverse cosine of x, okay, also known as arc cosine. So what is the domain of this function? So our domain has values from -1 to +1, and our range has values from 0 up to pi, okay, including both. So if we think about our unit circle, then only the angles from 0 to pi will come out of our inverse cosine function. So for example, if we have the inverse cosine of, let's say, √2/2. Okay, so we can read this as what angle between 0 and pi has a cosine of √2/2. All right, so to our unit circle we go. Cosine is our x's, and we've got a 45-degree angle that has a cosine of √2/2. Okay, so that's what I'm looking for. So in radians, pi over 4, or in degrees, 45 degrees. And that would be our answer for this simplified. Okay, tangent. Our inverse tangent, if we take just one period of our tangent function. Okay, so if we take the one that goes through the origin, which has a left vertical asymptote at -pi/2, another one at +pi/2, then this piece of our tangent function is 1-to-1. So if we take that, we restrict the domain from -pi/2 to +pi/2. Notice that those end values, those boundaries are not included since they're undefined. Okay, so if we take the inverse of that, reflected over the line y equals x, then we get this function here.
Oh, never mind.
Okay, 5 times. So we get, now we've got horizontal asymptotes, still goes through the origin, but what was our range has become our domain. What was our domain is now our range. So inverse tangent of a number, also known as the arc tangent, our domain is now all real numbers. And our range goes from -pi/2, okay, notice it's not included, to +pi/2, not included. All right, so on our unit circle, it looks real similar to our sine function. The only difference is that these two angles right here, our -90 and our +90, are not included in our range, okay, because they're undefined for tangent there. Okay, so just like our other two, if we have an example that says, let's look for the inverse tangent of 1. Okay, so what this is really asking is for what angle can we, what angle has a tangent of 1 between -pi/2 and +pi/2? Okay, so go into my unit circle. Now, remember, tangent of an angle is the same as the sine of an angle over cosine of that angle. So looking at our unit circle, if we're looking for the tangent of 1, anything divided by itself is 1, so where is our sine and our cosine the same? Okay, and it's positive, so they have to have the same sign. So that would be this guy right here. So 45 degrees or pi over 4. And that's in our range. So then this guy right here, we're looking for pi over 4, or in degrees, 45 degrees. All right, let's look at some more examples. Okay, so number 1, we're looking for the inverse sine of 1/2. Okay, so in other words, we're looking for what angle. So if we wanted to rewrite this, so we're looking for an angle. We're looking for the sine of what angle would give us 1/2. Okay, what is that angle? And remember, it's got to be for sine between 0 to pi over 2 and 0 to negative pi over 2. Okay, so sine 1/2, that looks like our 30 degrees, or in radians, pi over 6. Okay, we'll do radians from here on out. Okay, make sure you look at some directions will specify which units. If not, then you can choose either one. All right, number 2, inverse cosine of 0. So cosine is our x coordinate. So we're looking for angles, remember, between 0 and pi. So our cosine of 0 is at pi over 2. Okay, so now, again, 3 pi over 2 also has a cosine of 0, but it's not within our range. It's not within 0 to pi. Okay, number 3, inverse tangent of root 3. Okay, so remember, tangent is sine over cosine. So we're looking for some ratio that we get root 3 for. So I'm definitely looking at my 30 and my 60 degrees. If it's sine over cosine, then I probably want my root 3 on top. So let's try pi over 3. So if it's pi over 3, then that would be the tangent of pi over 3 would be root 3 over 2 over 1/2. Okay, if we multiply the top and the bottom by 2, then that would get rid of our denominators. By 2 over 2.
Carry tables, come to the attendance office. Carry tables to the attendance office.
Okay, root 3 over 1, same thing as root 3, so that's the angle that we're looking for, and that's within our range. So pi over 3 is our answer. Okay, number 4. We're looking for, oh boy, the inverse sine of the sine of 5 pi over 6. Okay, so we've got kind of a nested function here. We've got, on the inside, we're looking for the sine of this angle, 5 pi over 6, and then we want to take the inverse sine of that. So in other words, if we reread this, we're looking for what angle has a sine of the sine of 5 pi over 6. Okay, so let's start on the inside and work ourselves out. The sine of 5 pi over 6 is 1/2. So we can replace this, all this, with a 1/2. So now we're looking for what angle has a sine of 1/2. Now, we might want to just put 5 pi over 6, right? These two kind of undo each other. But the problem with that is that 5 pi over 6 is not within our range. If it was, we would be good to go. But it's not. So we need to find the angle that has a sine of 1/2 that's within our range. Okay, so that we reflect this over our y-axis, then we get our pi over 6 that also has a sine of 1/2. Okay, good. Let's do one more example together. And now we're going to go back to our right triangle trig a little bit. Okay, and look at a triangle example. So this one says, find an algebraic expression equivalent to the given expression. And we've got a little hint here. We're going to want to form a right triangle. Okay, so we're looking for the secant of the inverse sine of x. Okay, so we want the secant ratio of the angle whose sine is x. Interesting, so they don't give us any numbers. So without any numbers, it's not going to help us much to go to our unit circle. So we're going to need a triangle. So let's start with a triangle. Let's make it a right triangle. And let's put some angle theta down here. Okay, so we're looking for an angle whose sine is x. So now remember SOHCAHTOA. Our sine ratio is opposite over hypotenuse. So sine is opposite over hypotenuse. Well, the sine of this angle that we're looking for is x. So we can rewrite x as x over 1. The sine of our angle theta is x over 1. So we can use these as our opposite and our hypotenuse in this triangle. All right, so the side opposite theta we're going to call x, and then that would make our hypotenuse 1. Okay, so we're looking at finding the secant of this angle theta. So right here we're looking now for the secant of this angle theta. So now remember, secant is the reciprocal of cosine, so that's the same thing as asking 1 over cosine of theta. So we need to find the cosine of this angle. Cosine is the ratio of the adjacent to the hypotenuse. So we want our adjacent side, and we don't know our adjacent side. We know our hypotenuse is 1, but we got to find our adjacent side. So thankfully we've got a right triangle. We've got two sides. We can use Pythagorean theorem to find that third side. Okay, so let's set it up. So leg squared plus leg squared. We don't know what this guy is. Let's call him, I don't know, let's call him A. Equals 1 squared. Okay, so we're looking for our adjacent side A. So let's solve for him. So subtract x squared from both sides. 1 squared is just 1. Okay, we don't want a squared, we want a. So if we square root both sides, then we've got a is plus or minus the square root of 1 minus x squared. Okay, we can stick with just the positive of this guy. So we want root 1 minus x squared. That's our a value. Okay, so now that we've got an a value, let's plug that into our formula here. So we've got square root of 1 minus x squared. Okay, so we don't want to leave it like that. Now this over 1 is just itself, but we want to rationalize our denominator. So let's take our 1 over root 1 minus x squared, rationalize it. So we get square root of 1 minus x squared over 1 minus x squared. Okay, we can't simplify that any further. So our final answer, square root of 1 minus x squared over 1 minus x squared.
Mr. Jewett, please call main office, Mr. Jewett.
Okay, it's not very pretty, but it is an equivalent expression to the secant of the inverse sine of x. So if we knew what this x was, we could plug it in here and we could get the actual value for any x that falls within our range. Okay, so here are a couple of practice examples. If you want to practice some, we'll talk about these. We'll go over these in class tomorrow. And we'll spend tomorrow practicing our inverse trig functions.